The Poristic Triangle family has a fixed incircle and a green and a fixed circumcircle purple. Okay, this is a one-dimensional family of triangles that is inscribed in this fixed purple circle, and it's circumscribed about this fixed green incircle. Very good. And this family has been extensively studied since the 1800s or even 1700s. Many properties have been observed about it. Now here we're going to study a very interesting phenomenon. Let's go ahead and place a point Q on the fixed circumcircle. And I can choose the position of Q. Okay, now let me drop 3 perpendiculars from Q onto each side of the blue triangle. So I'm going to drop 3 perpendiculars onto each side, and the feet of these perpendiculars is represented by these purple dots. Okay, so these are the pedal points of Q onto each side. So here's a first pedal point. This is this construction line here is perpendicular to the blue side. Here's a second pedal point and a third pedal point. Because Q is on the circumcircle, a well-known result is that these 3 points are collinear. By the way, this point here is on the perpendicular of the extension of that blue side. This line is known as the Simson line of this triangle with respect to this point Q on the circumcircle. So if I vary Q along the circumcircle, I get a different set of collinear triples, okay, a different Simson line. A well-known result is that over all Q on the circumcircle, the envelope of these lines is known as the Steiner Deltoid, shown here. Okay, so you can see here that as I animate point Q, let's do this very slowly, the Simson line connecting the collinear points is instantaneously tangent to this deltoid. The 3 cusps of the deltoid define an equilateral triangle, and the circle that is internally tritangent or tangent on each one of these branches of the deltoid happens to be the 9-point circle of the blue triangle, which I can draw here. So here's the 9-point circle of the blue triangle. You can see that it's internally tangent, and if I move my triangle around, of course the whole system moves, but the size of this deltoid won't change because the radius of the 9-point circle is 1/2 the radius of the circumcircle. So since the circumcircle is fixed, the radius of the 9-point circle is fixed, and this whole object here is simply rotating and translating rigidly about x5, the center of the 9-point circle. Okay, so you can see that phenomenon there. That's pretty good. Okay. Now let's erase these things and let's talk about the main result here. Main result is the following. If I vary Q around the circumcircle, the envelope of Simson lines yields the Steiner deltoid. However, if I keep Q fixed and now I let the Poristic triangles traverse the family, okay, a very interesting phenomenon takes place. The set of Simson lines is actually turning about a fixed point. Or if you want to state it otherwise, all Simson lines that result from the system pass through a fixed point, Q prime. For example, if I move Q around a little bit, let's put it somewhere else. Let's put it over here. So now the fixed point is right here. I'm calling this point Q prime. And the Simson lines that get generated by the Poristic family all pass through this point. So that's pretty nice. The set of all Q primes over the set of possible Qs, their locus is actually an ellipse. So for all Q primes, if I move Q prime, for all Qs on the circumcircle, the fixed center of rotation of the Simson line set is going to lie somewhere on this ellipse. Okay, so let me leave Q here and let me animate the family. You can see there that the Q prime is sitting right there, sitting over here almost at the vertex of this ellipse. In fact, if I move Q down just so that it sits right at the vertex here, let's place it at 180. Okay, that Q prime is going to be at the vertex of this elliptic locus. Okay, Likewise, if I place Q over here, it's on the other vertex. If I place it at minus 90 perhaps, it's down here and that guy's over there. And if I place it at an intermediate location, Q is going to go over here. Okay, so this is the first really cool result. The second cool result happens, so let's go ahead and erase these objects. It's going to happen, similar result is going to be verified for the excentral triangles. So the excentral triangle, the sides of the excentral triangle are perpendicular to the bisectors at each vertex of a reference triangle. Okay, so I have this family of reference triangles, reference poristic triangles, and associated with each reference poristic triangle, I can draw its excentral triangle. The excentral triangle vertices are known as the excenters. A very interesting result is that over the poristic family, the locus of the excenters is a circle, i.e. the excentral family has a stationary circumcircle. And the circumcircle of the eccentric triangle is centered on its x3, i.e. the x40 of the reference triangle. This point here, the B1 point, x40, is the circumcenter of the excentral triangles. So you get this phenomenon. So that's pretty nice. Okay, oh yes, and the radius of this locus is actually twice the circumradius of the reference triangle. So we typically call the circumradius here big R. So the radius of the locus of the excenters is 2 big R. Okay, very well. Now, let's go ahead and light up a point P now on this locus, which is the stationary circumcircle of the green triangle. And if I drop 3 perpendiculars under, by the same token, these 3 perpendiculars are going to form a straight line. They're going to be collinear. Okay, so here are the 3 perpendiculars. This first point here has been dropped from P onto this side. This point here has been dropped from P onto this side. And this one has been dropped from P onto the extension of this green side. There it is. And you have this collinearity, the Simpson line of the excentral polygon. Now, of course, I can do the same thing. I can move my P around, and I'm going to get a family of Simpson lines. And this family of Simpson lines also envelops a Steiner Deltoid. Okay, so here's a Steiner Deltoid. Let's expand this a bit. You can see that you have this deltoid, so as animate my family, I get a rotating Steiner Deltoid. Now there's something really interesting here. The circumcircle of a reference triangle is the 9-point circle of the excentral. So the Steiner Deltoid's 9-point circle is this purple circle, and it is internally tangent to it at 3 points. The reason this is the case, that the circumcircle of the reference is the 9-point center of the excentral, is that you can see here that by definition, okay, the circumcircle is going to pass through each one of these points here, and these points, since the bisector here is perpendicular to these are also the feet of the heights or the altitudes of my excentral triangle, and the 9-point circle is defined also passes amongst all 9 points by the 3 feet of the altitudes. So you get this nice phenomenon, and now you're getting the fact that the Steiner deltoid of the excentrals is perfectly is a rigidly rotating object. No longer translates like the Steiner of the reference, and it's rigidly rotating about x3, the circumcenter of the reference triangles, which is congruent with, for the reasons just mentioned, with the center of the 9-point circle, x5 of the excentrals. Okay, all right, but this is not the phenomenon. The phenomenon lies on us not animating over the poristic, but not animating or not considering that deltoid over all p's on the circumcircle, but actually watching what happens to this Simpson line as I simply animate the poristic. So as I do this, the Excentral Simson line is moving for a fixed p, and this is also turning about a fixed point p prime. So we can see here a set of Simpson lines emanating from a fixed point p, and these are all passing through a common point P prime. Now you're going to notice that as I vary P, point P prime also varies, and that it is sliding, in fact, over the circumcircle of the reference triangle. So wherever I place P, P prime is going to be on the circumcircle of the reference triangle. Another very curious thing happens. P, P prime, and X1 are collinear. So I can draw a straight line between these three. And wherever I place P, I get this collinearity. Okay. So the set of Simpson lines from a point P on the circumcircle, on the fixed circumcircle of the excentral triangles, also rotates about a fixed point P prime that happens to be located on the circumcircle of the reference poristic triangles. Okay. Now, just to close it all off, let's go ahead and get rid of the construction, and let's place both Simpson lines on top of each other. You get a very interesting phenomenon. The Simpson line from a point Q, okay, that is co-located with P prime, this line over here, is perpendicular to this line over here. So the two Simpson lines are perpendicular for reasons we still don't understand. Thank you very much.